Hi everyone, my name is WeiQin, and today I'll be presenting our work on single domain generalization via normalized cross-correlation based convolutions. This work is a collaboration between RMIT University and Edith Cowan University in Australia. Machine learning algorithms are commonly built on the assumption that train and test data are sampled from IID distribution. However, such assumption is usually violated under data distribution shift or domain shift, which could be caused by changes in image style, illumination, background, and others. Some examples of domain shift are illustrated on the figure included on the right. When the IID assumption is violated, these models often perform poorly, as shown in the graph included at the bottom. When the severity of domain shift increases, the model accuracy drops drastically. To overcome the problem of domain shift, techniques like domain adaptation and domain generalization has been proposed. However, these approaches rely on other assumptions that hinder their practicality. For example, domain adaptation assumes the availability of unlabeled data from target domain for training. Meanwhile, domain generalization assumes the availability of multiple source domains for model training. So, what will happen if we only have a single source data for training? Single source domain generalization aims to solve this challenging problem. It relies on one domain for training, which is a very common phenomenon in practice. Current single source domain generalization approaches primarily focus on data augmentation techniques, aiming to enhance data diversity. In this work, we investigate another direction, that is to inject inductive bias into linear operators of deep neural networks to improve their robustness against domain shift. In deep neural networks such as convolutional neural networks, dot product is commonly used to compute the output of a layer L using an input X and a loadable weight parameter W, as shown in this equation here. However, from previous studies, it was found that the dot product operation is sensitive to changes in local energy of the input, as well as to affine shifts in the input, therefore making it not ideal for pattern matching, especially when there is domain shift across datasets. To overcome this problem, we propose XCNorm, which is inspired by the traditional template matching approach. XCNorm computes the dot product between the centered and the normalized weights and input, as shown in this equation here. To better illustrate the operation of XCNorm, we have included the animation below. This animation illustrates how the output of XCNorm is computed using a normalized weight and a normalized feature patch. In our studies, we found that XCNorm, although can effectively handle domain shift, is sensitive to outliers in inputs such as salt and pepper noises, which is also a type of domain shift. To overcome this problem, we propose to improve the robustness of XCNorm by integrating robust Welsh function to the input. The parameter c in the Welsh function was initialized to 1 and progressively updated using average of patch-wise standard deviation computed from the batch of inputs. Furthermore, we also propose to sharpen the output of our XCNorm operation using loadable parameter tau. This sharpening operation aims to emphasize the peaks and valleys of the output, as well as to eliminate the need for activation functions such as ReLU. As we also found that the normalization operation in XCNorm reduces the magnitude of gradient and thus slowing down the convergence, we propose to fix this problem using gradient scaling. In our implementation, we scale the feature outputs instead of the gradient to achieve the same goal but with more direct and simpler implementation. In addition, the patch-wise feature normalization in XCNorm assigns equal importance to all patches of the input, even for patches without useful class-relevant information. This can be problematic, as the model should be focusing more on patches that contain the class-relevant objects while ignoring the rest. To mitigate this problem, we propose norm-based attention mask, which uses a single XCNorm layer followed by a sigmoid activation function to map the patch-wise feature norm to patch-wise attention score. The attention score is then multiplied with the computer feature map to downweight the uninformative patches. Our methods achieve impressive improvement over the baseline in multiple benchmarks. For example, in the digits-DG benchmark, which is shown on the left, our XCNorm achieved 20.5% improvement over the baseline, and the robust variant further improves the performance by 4.39%, achieving the accuracy of 74.18% without relying on data augmentations. Then, by integrating data augmentation into our method, specifically the random convolution proposed by Shi et al., our method improved the baseline by 27.9% and achieved the accuracy of 77.15%, which outperforms all data augmentation-based approaches. The same trend is also observed in the Cypher10C benchmark, which is shown on the right-hand side of this slide. Our method also consistently outperforms the baseline by a respectable margin on medical imaging dataset Camion 17, despite training only on a single source domain. Some sample images from different domains in the dataset are shown in the top right corner. We also conducted an ablation study to better understand our proposed method. As shown in the table, the proposed XCNorm achieved 19.7% improvement over the baseline on the digits-DG benchmark. Then, including the norm-based attention mask further enhances the improvement to 21.4%. Finally, by integrating the robust Welsh function, further pushes the performance of our approach to 74.2% accuracy, which is a 24.1% performance increment over the baseline. We also studied the effect of the gradient scaling, which was proposed for mitigating the slow convergence issue. As we can see from the plot, including gradient scaling significantly speed up the training process, which is shown in the yellow plot, when compared to the model trained without gradient scaling, which is plotted in blue. We also investigated the sensitivity of our model to input perturbations using model robustness score as defined in this equation, where Xi represents the data augmentation function with severity S. When S is equal to 0, it means that no data augmentation is applied to the input X. Intuitively, if a model is robust against input perturbation, a model would estimate similar predictions regardless of the severity of augmentation and thus achieving low or close to 0 score, which indicates mutable perturbation sensitivity. As shown in the figure included below, we can see that the proposed XCNorm and its robust variant achieve substantially low model robustness score across all corruptions when compared to the baseline. This highlights the efficacy of our proposed method to enhance the model stability and sensitivity under input perturbations. In conclusion, in this work, we propose a novel technique to improve the conventional dot product in deep neural networks against domain shifts. Specifically, the proposed XCNorm provides affine shift invariance and energy change resilient as compared to the dot product operation, which is commonly found in deep neural networks. To further improve the robustness of our method, we integrated the robust Welsh function for effective outlier rejection and achieving boosted performance. Overall, our work provides effective methods for enhancing model performance and robustness, making notable contributions to the field of single-source domain generalization. If you are interested in our work, you can find our code in our GitHub repository using this QR code. Thank you.